Uh, yes, nice. Here with this, I would like to present our today's speaker, Oleksandr Dobrovolskiy from Technical University of Braunschweig, with his talk Fast Fluxons, Excite Short Magnons, and with one slide biography I would like to tell about him. Oleksandr Dobrovolskiy is professor and head of the Cryogenic Quantum Electronics Division at the Institute for Electrical Measurement Science and Fundamental Electrical Engineering at the Technical University of Braunschweig. He graduated from the Faculty of Physics of Kharkiv National University, and he received his PhD degree from Beverkin Institute for Low Temperature Physics and Engineering. Then he worked as a postdoctoral researcher and later as a principal investigator at the Goethe University Frankfurt for more than 10 years. Then he completed his habilitation in physics in Frankfurt am Main, and also in parallel he also defended the Doctor of Science degree also in our institute. Then he led the superconductivity and spectronics laboratory at the Faculty of Physics of the University of Vienna and represented Germany and Austria in several European networking programs. His research interests include superconductivity and fluxonics, magnetism and spintronics, three-dimensional nanostructures, hybrid systems, and quantum electronic devices, with many outstanding publications like last year's, which hopefully we'll learn about now. Oleksandr, please, with this, I would like to give the floor to you.
So can you see my screen?
Yes.
Yeah, thank you very much, Sergey, for the introduction. Thank you very much, Sergey and Andrei, for inviting me. It's my great pleasure to be part of this Kharkiv Quantum Seminar for many reasons. One of them is that in the past, my direct and strong link with the activities in Kharkiv, and I hope that we will be able to continue collaborations with different research institutions in Kharkiv. So today I am going to talk about Magnon-Cherenkov effect. The title has been formulated in a little bit punchy form: fast fluxons excite short magnons. And if my screen at some point will get frozen, this is a take-home message: fast fluxons excite short magnons. So I'm going to talk about the details of this fancy interaction. And I will begin with a brief introduction where we are located, which facilities do we have, and what are our activities and scope of research. So we are in Braunschweig. It's approximately in the middle of the northern part of Germany. And Braunschweig is a very special location for several reasons. There is a Technische Universität Braunschweig, so it's in English would be something like Institute of Technology. And there is a National Metrology Institute, PTB. And in recent years, there was established a new research center, which is called Laboratory for Emerging Nanometrology, with a few large equipments which can be used on the basis of mutual scientific interest. And we are located in this building, which you see. This is Helena and the Technical University of Braunschweig. So basically is in this whole house, the electrotechnics. So it's like building of electrotechnics. In our division, which appeared approximately 1 year ago, so we have 3 laboratories devoted to magnetotransport measurements, measurements at very low temperatures, millikelvin temperatures, but also doing spectroscopy at low temperatures. So basically 3 laboratories devoted to physics of low temperatures and electrotechnics at low temperatures. In addition to that, we have capabilities to conduct simulations, modeling, nanofabrication center, and as mentioned, a few larger equipments within the Lena Center. This is a team state of a few months ago. So there are still some activities conducted at the University of Vienna. By the end of this year, these activities and projects will be completed and mostly transferred to the location where I am currently here at the TU Braunschweig. The activities I'm going to present today emerged as part of the big collaboration FLUMAC project between 3 research groups, so in Poznan, in Czech Republic, and Vienna. The Austrian part transferred to the German part now, and we also benefited from the long-standing collaboration with the group of Michael Kut in Frankfurt, also in Germany. Okay, so we are doing research in physics, but are part of the electrotechnics, part of the faculty, which combines electrical engineering, computer engineering, and physics together. So our research is motivated by the current challenges in electronics. And as this header suggests, there are 3 pillar directions for the development of electronic devices. They should be small, fast, and consume low power. So the obstacle to achieve either of these goals is Joule heating associated with scattering of moving electric charges. And here on the left-hand side, it's a standard representation of the Moore's law. Nobody knows what will be in tens of years. Highlighted is a region for which I should plan our activities for the next 25 years. So basically, this is a limiting, so boundary condition given by the date of, by the year of my retirement. So we need to think how to develop technologies, how to combine technologies, because it is widely believed that it will be not a single technology, but a combination of those, which would allow to address this obstacle, minimization of scattering, and developing alternating approaches for information processing. In particular, possible strategies include to avoid scattering, which could be achieved by using electromagnetic waves, for instance, in vacuum, photons in vacuum. Basically, it's an example of non-dissipating motion. For electric currents in solids, one would require the superconducting state. Or to avoid net motion of electrons. And this approach is already exploited in spintronics, for instance, to operate with fields instead of currents, or to use spin precessions instead of spin currents. And regarding miniaturization, so currently it's a hot direction to extend 2D structures into the third dimension, talking about Sardinian architectures, where effects of geometry, curvature, and torsion not only allow to miniaturize and reduce footprints of structures, but also to explore effects related to topology and geometry in three-dimensional nano-architectures. For my today's talk, there are 2 pillars which will be important. So we will be talking about the combination of superconductors with magnetically ordered materials and the interplay of dynamic excitations, Fluxons, and spin waves in hybrid structures. With respect to superconductivity, there are a series of well-established quantum technologies. Examples include, for instance, superconducting single photon detectors. This superconducting strip, which is exposed to transport current, can be driven to normally conducting state, resulting in voltage pulse. And when superconductivity is destroyed, then the number of pulses contains the number about the photons which absorbed in the superconductor. It also can be applicable to detect both massive and massless particles, for instance, single molecules, because of their kinetic energy. Another application area is metrology. Josephson voltage standard, for instance, is based on Josephson junction, so superconductors interrupted by a weak link. And the further application of Josephson junction is here, is illustrated in this plot, so in this figure. It's what is called screed-on-tip superconducting quantum interferometer device, which is at the tip of some capillary, and this capillary can be scanned over the area of a sample under study. In particular, if one scans with such a sensor over the surface of a superconducting film, then one can recognize magnetic field maxima because of the stray field lights emanating from the vortex cores. And in the recent years, there was interest to combine cooperative states which are highly competitive, ferromagnetism with superconductivity to hybridize the order parameter. And in particular for thin film geometry, so here it's a cartoon, it's a sketch where a coplanar waveguide can be made, for instance, from a superconducting film, overlaid with a ferromagnetic material, and under resonance conditions, it can come to hybridization of modes, appearance of new properties which are not peculiar to the ingredients, so neither natural to the superconductor or to the ferromagnetic material alone. So this is a direction of the development of modern quantum technologies. With a particular further example, here just to measure emerging field of research, which is called quantum magnonics, for instance, where the excitations in the magnetically ordered state, so Kittel mode, it's a ferromagnetic resonance in a magnetically ordered material, can be coupled or read out to the state of a superconducting qubit. But not only in terms of Magnons, it can be any other sort of excitations, provided the conditions of strong interactions are met. Regarding magnonics, I need to mention a few words. So, what is a distinctive feature of magnonics with respect to spintronic and electronics counterparts? So, in electronics, the individual building block is electron. So it operates with charge areas which are moving, so there is net motion. In spintronics, one has additional degree of freedom, the electron spin in addition to the electron charge, and both this spintronics and electronics, they imply net motion of charge carriers. In magnonics, information can be encoded into the phase of a spin wave, so we are talking about a propagating collective precession of spins in material. And for instance, there are many approaches how to encode information with Magnons. One of them is to use the phase of a spin wave, where the logical state 0 would correspond, for instance, to phase equal to 0, and logical state 1 would correspond to phase equal to 180 degrees. So basically, here, this is the illustration of a magnonic device, majority gate, one of many possible devices, which actually attracted my attention back in the years to this activity when I was visiting the group of Andrei Chumak at the University of Kaiserslautern, and they were realizing this majority gate. So majority gate operates like this. So this is a table of trust. So there are combinations of input signals, and the output state is then dominated. It is determined by the dominating input state of this majority gate. And while the majority gate itself was of the order of a few centimeters, the phase setting elements were just standard built-in rack units of many tens of centimeters, like half a meter big phase setting elements. And we asked ourselves whether it would be possible to fabricate phase setting elements, phase shifters, which would be nanoscale and integrated on the same chip. The typical geometry here is shown in green. You see a substrate. On top of it, there are two antennas. In blue, one to excite spin wave, another antenna to detect spin waves. Spin waves are excited in a magnonic conduit, which bridges the space between these two antennas. They propagate from left to right. And in the middle of the antenna, if it is exposed to the action of a focused gallium ion beam can mill a part of the film to reduce its thickness. And in addition to that, it suppresses magnetization locally because of incorporation and stopping of gallium ions. So that these two parameters, conduit thickness and conduit magnetization, affect the spin wave dispersion, but also the group velocity, which is derivative of the dispersion relation. And this means that there isn't phase accumulation, so phase variation, which is additionally can be tuned by the applied in-plane biasing magnetic field. So this device is then reconfigurable depending on the strength of the in-plane magnetic field. And on the right-hand side, you see this is an example. It's a room temperature experiment. So where you have a permalloy film with two needles, or pica probes called. So basically high-frequency signal is applied through these needles, attached then to the respective place where antennas are located. and the rest we cannot see because the resolution here is not enough. The system is nanoscale. Yeah, basically this can be transferred also to low temperatures, and we now need to look at the details of what is particularly interesting in relation to magnonics if we have a superconducting film close to it. Most of technologically related superconductors are known to be of type 2. So in the phase diagram, there is a space where they are penetrated by vortices, mixed state. Just to remind what is a vortex, vortex can be viewed as a whirl of current surrounding the normally conducting core where the order parameter is fell down to 0. Magnetic field is at maximum as a vortex core and attenuates our length scale given by magnetic penetration depth. So fluxon, it's a one magnetic flux quantum carried by vortices in most of conventional superconductors, and repulsive interaction between vortices makes them to arrange to form a vortex lattice, which is illustrated in this cartoon. So the presence and configurations of vortex lattice have been visualized by using various experimental techniques, including scanning holes, scanning tunneling, scanning slit microscopies, and many others. In many cases, one deals with an ordered vortex lattice as here, so where you see almost like a vortex crystal. But because of interaction with edges, with imperfections, so with defects, with spinning sides, it can come to a deviation from a perfectly ordered vortex system. So one has an array or ensemble of vortices, but this ensemble doesn't necessarily possess a long-range order. And this will be crucial for the content of my talk, because we will need to ensure very high crystallinity of the vortex lattice when we're talking about coherent Fluxon-Magnon interaction. In particular, if one has a modulation of a magnetic parameter, for the propagation of spin waves, this media behave as magnonic crystals. What does it mean? If there is a match between a spin wave wavelengths and the periodicity of the system, then spin waves will be scattered, and because of destructive interference, like because of the break grating for solids, it should lead to the appearance of forbidden frequency gaps and allowed bands. So basically, it's a formation of block-like band structure. For fluxons, the major parameter which is of interest to us is this modulation of the straight field at the vortex core. It's at maximum. And when we have many vortices in a superconducting film, we have then a landscape of straight field, which will be acting on the magnonic waveguide. And here, this is just an example of one dispersion relation for Magnons, because it depends on the mutual orientation of the applied field and the propagation of the spin wave in the material. But this is just to highlight that so far, the typical parameters which affected the dispersion relation were width, thickness, and saturation magnetization of the magnonic conduit. So basically parameters which are defined and then kept constant during the operation of a magnonic device. And what we have been exploring during our studies is to use a stray field landscape, so biasing or effective field, which results because of the vicinity to the superconducting layer. And since the vortex lattice parameter can be tuned by tuning the strength of the applied magnetic field, that means that also the field and its modulation and periodicity can be tuned, and this allows us to introduce reconfigurability. So basically, an abricosal vortex lattice in a superconducting layer behaves as a reconfigurable, tunable break grating for the propagation of spin waves. And on the right-hand side here, this is just an exemplary plot of spin wave transmission spectra with indicated band gaps, first and second order, because of break scattering of spin waves on the rows of abricosal vortices. And these band gaps evolve as a function of magnetic field approximately as 1 over square root of b, where 1 over square root of b is just the abricosal relation for the vortex lattice parameter as it scales with increasing magnetic field. But in addition to that, not only the field, we also have the degree of freedom dictated by the transport currents. So if we apply a transport current to a superconducting field at currents which exceeds the dp current, the vortex ensemble will be set in motion. So this magnetization or stray field landscape will be displaced from left to right, so in the direction perpendicular to the transport current. That means that we will have two possibilities. Spin waves and vortices move in the same direction or in opposite directions. And in addition to block-like band structure, there will be shifts because of the Doppler effect. Yeah, and this Doppler effect can be direct or reverse. It also depends on the peculiarities of the dispersion relation. Because for Magnons, for spin waves in a particular geometry, which is called backward volume magnetostatic spin waves, it is possible to have a negative group velocity. But today I'm not going to talk about the Doppler effect. We would like to take a look at what is happening when vortex motion is at high velocities and when such a superconducting layer is overlaid by a Magnonic conduit. This brings me to the topic of my presentation. So why to generate Magnons? Why do we need them? And why do we need in particular short wavelength Magnons? Why this is attractive, interesting, and challenging to excite. So we take a look first at the dispersion characteristics. So the major characteristic describing spin wave in a system is a relation between the frequency and wave number. You can interpret as energy and momentum characteristics. And generally, you have at least two different regimes. In the regime of long waves, you are talking about dipolar waves, and this regime was mostly investigated so far. In the dipolar regime, the dispersion characteristic is very anisotropic, so it depends on the mutual orientation of the biasing field with respect to the direction of propagation of spin waves. And the dispersion doesn't start from zero. It starts from a particular frequency point. The physical meaning is a ferromagnetic resonance. So you have a well-defined frequency which corresponds to uniform precession in the limit when k is equal to zero. In the opposite Lipantine case, you going to reach the exchange regime, where spin waves will be characterized by parabolic dispersion. And this regime is interesting because spin waves are short. We are talking about wavelengths of the order of few tens of nanometers, because we want to develop and to operate with nanoscale Magnonic devices, which themselves are small, so the respective building blocks, Magnons or spin waves, should be characterized by respectively short wavelengths. But because of the shape of the dispersion characteristics, you see here, because of the parabolic dependence, also the derivative, this curve becomes very steep. And this means that also the group velocity is very fast, and we are in the kilometers per second range. So there are two major characteristics of exchange-dominated spin waves. They are characterized by short, so nanometer scale wavelengths, and velocities of the order of kilometers per second or even more. And this brings me to a challenge, how to excite such spin waves. So typical design for experiments in magnonics, you have some magnetically ordered material, so Magnonic waveguide. One antenna is used to excite spin wave, another antenna is used to detect spin waves, and the wavelength is determined by the double width, because you are talking about the magnetic field component at the edge with pointing upwards or pointing downwards. It's like half wave. So if you want to excite 50 nanometers long Magnons in terms of their wavelengths, the width of the conductor should be of the order of 25 nanometers. And even with today's state of the development of e-beam lithography, technically you can have such a feature size in the fabricated antennas, but even if you use gold antennas, then the sizes of the antenna become comparable and even less than the electron mean free path in gold as a material. This results in drastically increasing resistivity, And as a consequence of this, very high microwave losses and poor impedance matching and very low spin wave excitation and detection efficiency. So alternative approaches need to be developed, and fortunately, nature shows us further examples, and the most familiar probably is the formation of a Kelvin wake behind an object which is moving on the surface of water. Yeah, it's a very interesting example actually, because the idea is to have at least one crossing or touching point in the dispersion characteristics for excitations in both systems. So this is our mechanical object. Water, it's a different system where there are water gravity waves which exist there. They are characterized by this dispersion shown in red. And the shape of this dispersion actually answers the question why it doesn't matter how fast, what is the velocity of our finger when we approach the water surface. In all cases, we will excite a wave. Because for this type of dispersion, for this shape, there will be a crossing or touching point, and there will be generation of waves, excitations of waves. But for spin waves, that will be different, yeah, because we have the gap associated with the ferromagnetic resonance. So we will have to overcome, we will have some kind of threshold condition, and this threshold behavior is also known in the context of high velocity excitation rooted in the context of Cherenkov radiation, formation of Magnons, which I'm going now to review in the form of a quite a short historical retreat. So basically, this problem of generation of waves dates back to the works of Lord Kelvin, shown on this slide, who investigated the formation and shapes of waves behind a moving boat. And the conditions were, so he assumed that there is no surface tension, turbulence, there is linear superposition of waves because he got two solutions. And this solution was applicable to a deep water dispersion relation, so basically dictated by the gravity, so acceleration. So no matter the speed of the boat, it should produce a wake with a wake angle alpha of around 90 degrees. That was the primary message. But very similar phenomena appear also in other systems. And if we now leave the domain of air, the domain of hydrodynamics, we can also take a look of what is happening in the relativistic regime of fast-moving particles. So basically, this links with the motion of electrons, with the prediction of Sommerfeld consideration, what will be if the electric charge is moving at velocity exceeding the speed of light. It should radiate. Unfortunately, the counter argument was that electric charge cannot move at velocity exceeding the speed of light, talking about vacuum. But in media, light, so basically the speed can be exceeded because of a different propagation velocity, which is here divided by the refractive index. And that was experimentally observed as a blue light from water upon radiative bombardment after sources of fast-moving electrons had become accessible. And this is an example from relativistic dynamics. So what is interesting here for the Cherenkov radiation of electromagnetic waves, this Cherenkov angle is related to what is called self-synchronization condition. So basically, it's a very interesting case one can consider just upon a geometrical consideration. I'm going to dwell in a minute in detail, where when the velocity of the particle which propagates will be equal to the velocity of the excitation it gives rise to. It's a very special, very interesting case, and it is exactly this case which is relevant to the coherent interaction of fluxons with Magnons. So now I would like to move to magnetism, and as a source we have a pulse of magnetic field which will be propagating along a magnetized magnonic waveguide. So far, this topic was only considered theoretically before recently. Experiments then confirmed the existence of this effect. But the major prediction is if a magnetic pulse is propagating here, as shown from left to right, it should come to the generation of two waves, one in front and one behind the moving surfaces. And these waves will have different wavelengths. So I try to start the animation here on the basis of micromagnetic simulation. This illustrates the Cherenkov effect in the context of magnonics. Yeah, as a theoretical model, it was very interesting and fruitful in terms of results and predictions, but no magnetic sources which can move at high enough velocities were available so far. And for the experimental realization, it was necessary to find a respective system. And in addition to that, one has to consider three different regimes. So basically, if the source moves with at velocity which is lower than velocity of excitation, we would just have a Doppler effect. It's already investigated already in the first experiments of Magnon-Fluxon interaction. In the opposite limiting case, when velocity of excitation is lower than the velocity of the moving source, we would have like a Mach cone, what we have seen, for instance, for water waves, Kelvin wave. We can also this expect for Magnons and Fluxons, but the results I'm going to present today are related to this self-synchronized regime when the source speed is equal to the velocity of excitation. This corresponding exactly to the shock wavefront synchronization. So basically, for vortices in superconductors, obviously we have many sources. And then this self-synchronization condition is very important in order to preserve the long-range order of the moving vortex lattice. So basically, as illustrated on the left-hand side, even if there are deviations in the periodic arrangement of vortices, the generation of spin wave acts back on vortices, and by inducing eddy currents, the vortices are adjusted to form straight rows to be moving in phase, and this leads to kind of resonance enhanced interaction with the generated spin wave. In terms of the dispersion relation, the underlying dispersion relations look like that. So spin wave here in red, it's a parabola, and the vortex lattice is characterized by linear blue. Here it's a straight line. The physical meaning for the respective dispersion relation, it's a washboard frequency of vortex motion. If you have a pen or just with a finger, you can move our keyboard of your computer. And if you will be moving faster, the frequency which you listen to will be higher. Or if you, for instance, increase space in between the buttons on your keyboard, the frequency will be low. So basically there are two parameters, vortex velocity and vortex period, which affect the washboard frequency. And this type of interaction, so having a crossing or touching point for two dispersion characteristics, were already investigated, for instance, for the interaction of magnons and phonons in a different physics context. But in contradistinction to ordered systems, vortices, as shown here, as ducks, so they should be actually properly located. If some vortex will be located improperly, there will be destructive interference, so care should be taken regarding the long-range order, like perfect crystallinity for the vortex, for the moving vortex lattice. So first thing to check is whether we are able to detect microwave excitation from vortices or spin waves with high enough sensitivity, and whether vortices can move in a coherent fashion. So some preliminary experiment was conducted. So in yellow here, you see a superconducting layer, which was overlaid by a normally conducting gold antenna formed as a meander-shaped nanowire. There were no direct electrical contact between the antenna and the superconductor. They were just stray field coupled, so inductively coupled. And the magnetic field, which was perpendicularly oriented to the superconductor plane, populated the individual antenna periods with vortices shown like that, which corresponds to commensurate state. So every vortex row corresponds exactly to one period of the antenna. This was needed for that all vortices would contribute in phase, and the entire signal would be just a sum of individual antenna periods. And then, by applying a current from left to right to the superconductor, the vortices were displaced from top to bottom in the plane of the screen. So vortices are looking to us, but moving from top to bottom. And with increasing of the transport current, there was appearance of some maxima, some peak, which was detected by the antenna connected to a high frequency oscilloscope, with even two modes observed, with higher frequency mode attributed to the crossing of individual antenna periods, and low frequency mode related to the full crossing, so time of flight from this bank to this bank completely of the antenna structure as a whole. So typical frequencies were already in the proper frequency range, low gigahertz frequency range. And another question was whether some other approach can be used to enhance the periodicity of the vortex structure. So we considered not the periodicity of the antenna, but periodicity of the structure itself, which was composed of a superlattice of 50 double layers of molybdenum and silicon, with current applied this time in plane from left to right in the plane of the screen. Magnetic field applied as shown here to the into the screen, and resulting in the vortex motion from bottom to top. And this geometry is shown in this cartoon. So basically, this is just an electronic scanning electron microscope of where the many layers are located, but they are not seen in the scale of the image because of very low contrast and the scale bar here. So just like 5 nanometers for the pair of molybdenum and silicon layers. Again, the experimental observable was just microwave power detected with a coaxial loop antenna placed in the vicinity of this multi-layer system with frequencies in the tens of gigahertz range. But so far, these effects were observed for vortex velocities in the sub-kilometer per second range. So the coherence was good, but the vortex velocities were not yet enough to think about their combination with the excitation of spin waves, because we need first to approach to touch the dispersion characteristic above the ferromagnetic resonance frequency. Well, if one wants to accelerate vortices to higher velocities, typically what is measured experimentally, it's a representative series of current voltage curves for a type 2 superconductor in the mixed state. What you see here, it's a series of abrupt jumps. Yeah? So this superconducting transition is not continuous, it's not a regime of nonlinear superconductivity, but it's just a sudden jump. And the idea is how to tune the properties of the material in order to realize higher voltages, higher velocities, while providing the possibility for the vortex lattice to maintain its long-range order. So at this last resistive point in the flux flow state, before the jump to the highly resistive state, these are results of time-dependent Ginzburg-Landau modeling. You see that blue color corresponds to the nucleation of normally conducting phase. So basically, superconductivity is destroyed first at the edge, where vortices enter the sample. And you see here already deviation from the expectation to have a perfect vortex crystal. You see that long-range order is here lost. And the microscopic reason for that is the phenomena called flux law instability, described theoretically by Larkin and Ovchinnikov. The idea is that the vortex core, which contains unpaired electrons, for these electrons, this very high velocities mean that these electrons acquire kinetic energy, which becomes comparable with the potential energy variation at the vortex core and around it. So these electrons can escape from the vortex core, and the vortex core shrinks. And while driven by the same driving transport current, a narrow vortex can then be accelerated faster and faster. It's kind of a positive feedback. That means like avalanche-like acceleration of vortices leads to abrupt destruction of the superconducting state. Still, there are measures which can be taken to suppress the nucleation of flux flow instability. It was a matter of research over more than a decade, yeah, which is summarized here in this phase diagram. So there are lots of different mechanisms close to TC, far away from TC. I don't have time to comment on this. This is summarized in this 10-page review. But the idea is that in principle, it's possible to tune quasi-particles relaxation time and to operate with one of them dominantly. For instance, the electron-phonon interaction close to TC, or it's a hot electron regime, electrons dominating scattering range far away from TC, to use superconductors with very strong and close to ideal H barriers for the ordered vortex motion, and in general, dirty limit superconductors, which are materials of choice for photon detectors, as stated here. Instability velocity is inversely related to the relaxation time. So basically all materials which are good candidates for single photon detectors, they are characterized by short relaxation time, and such materials also support high vortex velocities in the kilometers per second range. And one of possible realizations, yeah, I just remind what we need to reach. We need to have this green touch or crossing point and the dispersion characteristics to have this Cherenkov-like resonance condition as illustrated here, so that a wavelength of spin wave will match the distance between vortices, and also the frequency of the spin wave will be equal to the washboard frequency of the moving vortex lattice. So we are talking about frequency, so energy and momentum match, in other words. And these materials were realized by direct writing under the action of focused ion beam induced deposition. It was possible to fabricate niobium carbide strips, which are characterized by close to perfect H barriers for vortex entry. This material additionally is characterized by very short quasi-particles relaxation time, weak volume pinning, and high critical current. So in principle, it's possible then to apply such currents, which are accelerating vortices to very high velocities. And to give you idea just about the numbers, even 10 kilometers per second can be realized, 5 kilometers per second, especially in the regime of high fields, which is enough or even more than enough for our purposes. It would be enough to have just something around 2 kilometers per second or 1.5 kilometers per second for the spin waves we are going to generate. And in independent experiments by other groups, the very high vortex velocities were also directly imaged for different materials. For instance, by scanning slit of tip microscopy with vortex velocities reaching of the order of 40 kilometers per second now. And there are continuous reports to enhance this value just in the course of later investigations. Good. So now we are moving to the fabrication of Magnoni counterparts, because our superconductor was directly written in dual beam scanning electron microscope. The same setup was used for the fabrication of magnetic structures. So this is an example of a ferromagnet, BCC phase of cobalt iron. Feature sizes can be controlled with very high resolution, but the resulting structures are of the order of micrometer, so sub-micrometer range. They can also be what is shown here. These are three-dimensional individual building blocks, which we call nanotubes and nanotrees. And in these animations prepared by Marcin Winholt in the group of Michael Kut at the Goethe University of Frankfurt, this is just an idea of the process. Dual beam scanning electron microscope with a chip mounted onto it, where there will be a fabrication of structure by means of focused electron beam induced deposition. So into the electron chamber here, you see a gas injection system, which is introduced. And this gas injection system is used to let a precursor gas into the microscope chamber. And then, under optimal conditions, so shaken by thermal diffusion, these molecules of precursor gas are shaken in the vicinity of the area where the sample is going to be fabricated. The operator defines a pattern file, and then the focus beam is scanned over the surface of the active area in accordance to the predefined landscape. The volatile components are pumped away from the microscope chamber, and the remaining deposit is a sample which then is going to be investigated and used for further studies. So in this case, this is exemplified for platinum growth. We use this technique for cobalt iron for the magnetic conduit and niobium carbide for the superconducting counterpart, and combine these materials together. This brings me to the experimental realization of the system. In blue, you see the niobium carbide superconductor to which DC current is applied experimentally. In rose color, this is an insulating layer. So superconductor was covered with a buffer insulating layer to avoid proximity effect, so that vortices would be coupled only inductively, electromagnetically, if you like, with spin waves in the orange conductor on top. And then spin waves, if they are generated, they are propagated from left to right to the area where there is a microwave ladder antenna connected to a spectrum analyzer, and spectrum analyzer is then used to monitor any high frequency signal which is associated with the propagating spin waves. So I just want to emphasize that we do not apply any AC current to the superconductor. It's only driven by DC current, and the propagation of the vortex lattice in the superconductor itself, it induces spatial and temporal modulation of straight field in this hybrid region. And when the matching condition is satisfied, is illustrated here in panel B, then it comes to generation of spin waves. The spin waves can be directly detected by the microwave antenna, as shown here on the right-hand side. And in addition to direct detection of the spin waves by the spectrum analyzer, we also monitor the current voltage curve of the superconductor. And in the regime of Magnons generation, it's interesting to observe voltage plateaus, which in the context of superconductivity immediately resemble something related to Shapiro steps. So these voltage plateaus are a fingerprint of some coupling between excitations, like two oscillators, as similar for Josephson junctions, irradiated, for instance, by microwaves, or vice versa in the regime of generation. There is this coupling regime as well. And also, these steps are occurring in the flux flow regime, but usually, if you extrapolate the quasi-linear regime, it means that there is missing increase in voltage. And the reason for this missing increase of voltage means that energy from the superconductor is spent towards the generation of spin waves. So generation of spin wave cool down superconductor, and this can be seen also directly from the vortex velocities, so maximal vortex velocities, which determine the nucleation of the flux flow instability state. So basically, generation of spin wave stabilizes the vortex lattice, suppresses instability, and this effect is actually was predicted as a Polaron type mechanism for the moving vortex lattices. And additional interesting feature is, if we take a look at the frequencies of the generated Magnons and express these voltages from the Shapiro steps as divided by frequency and the number of vortices knowing the area for the magnetic flux treating the hybrid region, we deduced one magnetic flux quantum. So basically, this Cherenkov resonance threshold condition corresponds basically to the Josephson relation if one takes into account the number of vortices participating in the Magnon generation. Another interesting feature is that with radiation of Magnons, maximal vortex velocities are now higher because more heat is removed from the superconductor. And this is in line with the prediction of these Polaron-like vortices, where there is a strong interaction of Magnons with Fluxons, whose presence and motion has led to their appearance in the material. I'm moving to some interpretation with the help of analytical Kalinikov's line theory to show that there is a joint crossing point in the dispersion of both Fluxons, linear characteristics, and Magnons, parabolic characteristics, with this very bright area corresponding to the strong interaction, so crossing of the two dispersion characteristics. Micromagnetic simulations based on the solution of Landau-Lifshitz-Gilbert equations support these observations. So additionally and visually, we have here the propagation of spin waves from left to right. It's kind of Magnon beam or Magnon torch, if you like, with very interesting properties of this Magnon generation. It is unidirectional, so spin wave propagates in the same direction as the moving vortex lattice. Generated spin wave is with a wavelength which is determined by the periodicity of the vortex lattice, and this interaction is coherent. It is shock wave protected phase because there is a back action of the spin wave which induces eddy currents, and this eddy currents couple to the vortex lattice which moves via the superconductor. So basically what we have got, in addition to just hunting for the possibility to generate Magnons, it was possible to realize a new approach for the generation of Magnon beams. And this is also interesting direction because many things were predicted in Magnonics on the basis of known phenomena in optics. For instance, graded index Magnonics was introduced a few years ago. Steering of spin wave beams was suggested by various means to investigate reflection, refraction, diffraction effects, mirage effects, and so on. And now at our disposal at lower temperature yet, but we have the possibility to unidirectionally excite spin wave beams and then to investigate their propagation in Magnonic conduits. In terms of the wavelengths, it is interesting to compare that during many years, so 5 years, it's taken people to just increase the K vectors by factor of 2 extensively by using some graded coupler approaches or reducing the size of microwave antennas. But now, because of this paradigm shift, just transferring this towards Fluxon-Magnon interaction, we have achieved K vectors of the order of 180, so basically by factor 2.5, beating the previous records and now having at our disposal wavelengths of the order of 35 nanometers for spin waves. And the next question is where to develop this concept further and which systems to operate with. So far, my consideration was mostly related to vortex lattices and their global dynamics, but having, for instance, a notch, it would be possible to inject vortices into the superconductor locally to have different configurations. For instance, an individual vortex, 2 vortices, or 3 vortices, which, because of repulsive interactions, would form a vortex jet. And this particular configuration is very interesting because if one has, for instance, ferromagnetic disk with spin waves, it's like shooting using 2 guns, left, right, left, right, left, right, to introduce a particular frequency for the parametric resonance excitation of spin waves in magnetic nano elements locally. And we have also developed approaches how to count fluxons on the way to the realization of this regime. So as the next step would be to take a look at the structure of vortex cores of individual fluxons, especially in the regime of high velocities, but also to operate with various configuration of fluxons to have hybrid systems where a particular configuration of fluxons would have particular features in the Magnon frequency spectrum in hybrid devices with additional links to other fields of research extending to, for instance, electric field control, collaborating with people from semiconducting technology or optical control, from people that are inputs who are doing optics at low temperatures. So this is like a platform which allows for plenty of collaborations. And at some point, I hope we will have also interesting results emerging from this planned studies. This brings me just to a brief announcement that there is a recently published roadmap on nanoscale superconductivity for quantum technologies, vision of the community of a few directions where the field is going to be and how it's going to be shaped in the nearest future. But there is also some insights, especially devoted to school age children, teenagers, in the format of an escape game, also translated in Ukrainian. So if there's interest, the book is available for some small amount via Amazon, for instance. This brings me to a summary of my presentation. So there was quite a set of works devoted to the optimization of ordered vortex lattices, which could be achieved, for instance, by having periodic antennas, periodic intrinsic structures, in order to get sufficiently uniform vortex lattices. The approach which worked best is to have a superconductor in the duty limit, but still which is quite uniform and support vortex velocities better in the order of 10 kilometers per second. And then, in addition to, for instance, Doppler effect in the regime of low velocities, in the regime of high velocities, it was possible to excite spin wave by using Cherenkov-like regime of radiation. The physical meaning is a matching of energy and momentum or frequency of wave vector, in other words. So condition of self-synchronization or condition of Cherenkov resonance for strong Fluxon-Magnon interaction with wavelengths of the order of 35 nanometers as record values achievable so far. And we developing approaches towards single flux quanta and the operation in 2D and 3D hybrid system, meaning that further hybrid systems should emerge also on the basis of these platforms. So this brings me to my conclusions, and I'm very much open to your comments, questions.
Sasha, thank you so much for the very beautiful presentation and for the instructive talk, which is now open for questions. Let me start, Sasha, from asking about the Shapiro steps. Can you tell more about the analogy between magnonic and conventional Cooper pairs, Cooper pair Shapiro steps? Do magnons play the role of Cooper pairs? Which characteristics magnonic Shapiro steps have?
So basically here we take a look at the voltage, and this voltage corresponding to the Shapiro step is expressed in the units where we know the number of fluxons and we know the Shapiro, we know the spin wave frequency. So this is very similar to Josephson relation, just frequency and phi naught would be Josephson junction. But here, in addition to that, we have number of fluxons. So if we have Josephson effect, we have relation of frequency of electromagnetic radiation and voltage. And this is linked by the fundamental Josephson constants of basically phi naught. In our case, it is the same fundamental constant of magnetic flux quanta, or 1 over phi naught, it's Josephson constant, it is the same. But in addition to that, we have number of fluxons. That means that all fluxons which are available in our system contribute coherently, but now instead of the frequency of electromagnetic radiation, we have the spin wave frequency. The rest, the voltage over the superconductor, it is the same.
That's very nice. And about quantumness, closer to the end, you've said about the quantum regime. Where's quantumness here?
Yeah, so basically, in the regime of very low temperatures, and especially for materials in quantum limit, the electronic states within vortex cores, they will be quantized. And there are Bloch oscillations observed or largely predicted, but for some materials already observed in the limit of very low temperatures for vortices, which are moving. So basically, the internal electronic structures of the vortex cores can be deduced on the basis of features observed macroscopically via measuring the current voltage curve of the materials.
Thank you. More questions? Yes. Oleg Georgievich, please.
I have such a question. Is the periodicity of the vortices which accelerate still good? Still it keeps this periodicity keeps the same as for low velocity vortices? I think that the interaction between vortices become weaker when they become thinner at high velocities. So maybe periodicity then should be deteriorate.
Yeah, thank you. Very good question. And actually, I have flashed this backup slides prepared to answer this question because it was our major concern. What will be a drawback of lacking periodicity in the moving vortex lattice? And it turned out, actually, it doesn't matter. So what I mean is that in principle, one can begin with an ensemble of vortices like here, for instance, shown, without Magnons. And then it would come to the nucleation of flux flow instability, so superconductivity would be destroyed. But if, because of this magnetic dynamic interaction, there is a formation of spin wave naturally possesses a periodicity. And the periodicity of a spin wave imprints a dynamic pinning landscape to keep vortices at exactly symmetric ideal position, so to say. So basically, after a few periods, it comes to the formation of such stripe-like patterns. So vortices, instead of being like moving chaotically, are arranged in these extended stripes. Here you see like channels. They even break the symmetry. So basically, in all our relations, it turned out that not the hexagonal, like abricos of corrected formula, should be used, but just like a square lattice, where the periodicity is actually the distance between, not on the basis of the hexagonal elementary shape or triangular elementary shape. That this is just a distance between vortex rows. So basically, the spin waves imposes a dynamic pinning landscape, and this dynamic pinning landscape is then synchronized with vortices. So vortices are automatically phase locked, arranged because of the presence of the spin wave, which is generated because of their motion. So this is condition of self-synchronization.
Very, very interesting phenomena. One more question about vortex rivers. Are the vortices still individual in these rivers?
No. It's a dynamically formed Josephson junction. So if we are talking, I didn't mention that because of lack of time, but so if we accelerate vortices, what is happening first? So if we apply stronger current, there are many vortices nucleating, but they are still going one to the left, to the right, left, right, because of repulsive interaction between them. There may be more than 3 rows of vortices, can be 3 or 4, doesn't matter, but they are divergent, so to say. If we continue to increase the driving current, then the time of flight will be shorter. So perpendicular component of the velocity will be higher and higher and higher, and vortices will not have enough time to open the angle, so divergent angle for the vortex jet. So they will be sticking together, and electrons, which will be escaping from the vortex course, will lead to their attraction. So these two opening vortex rows, which are like divergent to some extent, they will be sticking together and forming one single vortex river. Vortex river, it's a dynamically formed Josephson junction, where the order parameter is only slightly modulated. So vortices like Josephson, they are moving in a very fast.
The course overlap.
Yeah, the cores are overlapping. And also there is a topological transition for the screening current. So there is a global screening current, like in a wide Josephson junction. Yeah. And also for microwave characteristics, there is a jump in frequency because you don't have this factor n corresponding to the number of vortices, but now you have a Josephson frequency.
Maybe in other words, this is the same that phase-slip line.
Yes, it is a phase-slip. Exactly, it is phase-slip line. Just other words. Yeah.
Okay. Thank you.
And this works only if there is good heat removal. But typically it can be a limiting condition. If the heat removal is not enough, then instead of facelip line or vortex river, especially for dirty limit materials, we will have a normally conducting domain which will grow.
You have quantumness in many places, in particular in the name of your group, cryoquant.
Yeah.
Nice. More questions? Then, Oleksandr, thank you so much for being with us today, for your nice talk. We hope to see our attendees in 2 weeks. Then all the best to everybody.
Yeah, thank you so much also from my side.
Bye-bye.
Bye.
Thank you for the interesting talk. Bye.